Kia ora, Year 11 and 12. This is another request from Aidan for a question about partial fractions and a binomial expansion. So here's the question here. Now, Aidan's only asked me for help with the last bit, but I'm going to go through the whole thing so that we get some revision of partial fractions and then some nice integration stuff, and finally a very messy but straightforward binomial expansion problem. So the first thing I want you to remember is that we have quite a few different patterns for the partial fractions, and this is one where we've got a quadratic term in the denominator, and it's a 1 plus x squared term. So that means that we can't split that up by factorising, and that gives us one single term here with a linear factor on top of that. So if that's not making sense, it's time to go back to chapter 7 and revise it. I'm pretty sure it's the last pattern type that we looked at because it is a bit weird, but you can see that what's going on is that when I cross multiply here and here, if I'm going to generate a quadratic term in both places, I need to have a linear times a linear here, and then I'll have a quadratic when I have the constant times the quadratic here. I'm sure that was about as clear as mud. Anyway, let's get going. So we do the usual thing. We set up f of x. So we've got 16 plus 2x plus 15x squared over the denominator. And we need to find the values of a, b, and c that are going to make it work out. So we've got a plus bx over the quadratic thing plus c over the linear factor of 2 minus x. And we're told that a is going to be 0, so that's useful. There's no excuse for getting this one wrong. Let's start, as usual, by just focusing on the numerator once we've got the common denominator here. So we're going to have a plus bx times 2 minus x plus c times 1 plus x squared. So I usually like to start these with substitution, and we're going to substitute in x equals 2 on both sides. And from there I'll do matching the coefficients. So if we let x equals 2, we get 16 plus 4 plus 15 times 4 is 60 is equal to 0 from all of this, because that one's 0, plus c times 5. So that gives me 80 equals 5c. C is equal to 16. Right, so now I can't do matching. I can't do substitution again on this one because there's no x value that will make this factor 0, so that's a bit of a pain. What I'm going to do instead is I'm going to substitute in the c as 16 here, then I'm going to expand all of this out and then match coefficients. So it's not too bad. You just have to not freak out when you can't do this, making this one 0. So on this side we've still got this, and over here we've got a plus bx times 2 minus x plus 16 plus 16x squared. So now we'll expand out this bit and we get 2a plus 2bx minus ax minus bx squared plus 16 plus 16x squared. So we can now match coefficients, and we can see we've got 16 here. So I'm just going to write a word to show the person reading what I'm doing. So matching, I get 16 is equal to 2a plus 16, right? So what am I doing? Well, I'm picking out the constant terms in there, and that means that a must equal 0 as required. Now we can match the 2x, so 2x is equal to 2bx minus 0x. So I'm matching the x terms here. That gives me 2 is equal to 2b, so b is equal to 1. So that's good. That means we're ready to start on the second part of the question. Right, so we've found b and c, and now we want to use that partial fraction thing to make integration much easier. So we're on to part 2. So when I integrate f of x, I can now write this as follows. It's the integral of bx, so 1x, x over 1 plus x squared, plus c, 16 over 2 minus x dx. So let's spot the pattern that we've got with this first one here. Well, I've got a quadratic in the denominator, and I've got a linear thing, x, in the top line. So that means that it's going to be easy to integrate that back to a log. So leave a gap. It's going to be something log of 1 plus x squared. Now, when I differentiate this, I'm going to get 1 over this, which is good, but I'm going to get times 2x by the chain rule. I don't want 2x, I just want x, so I need to multiply by a half. Similarly, in here, I'm going to have something log of 2 minus x. And this is all evaluated at 1 and 0. But when I differentiate this, I'm going to get 1 over the 2 minus x, which is good, but I'll get a times negative 1. So I don't want that. I need to have minus and minus 16 of that. Okay, so that's the anti-differentiation done. Now we just have to do the substitution. So substituting in gives me this. I get a half of the log of 2 minus 16 log of 1 minus a half log 1 minus 16 log 2. That cleans up to give me a half log 2 minus 0 plus 16 log 2, giving me a final answer of, this is 32 over 2 and this is 1 over 2, so 33 over 2 log 2. All right, so we're at 6.5 minutes already, and we actually haven't started the muckiest bit of this question. So this video might go on to a second video, sorry. Let's go back and see what we had to do. Oh, wrong question. Where is it? Okay, so here we go. So we've done the partial fractions expansion, right? And that wasn't too bad because we've got a as 0. Now we have to do f of x as a sum of powers of x up to and including the term in x to the power of 4. But we're not going to use this. We're going to use the partial fraction expansion. And we're going to get two separate binomial expansions and quite carefully put them back together just up to the term in x to the power of 4. To determine the range of values for which it's valid, I can do that before I get started, right? So remember that binomial expansions work. Let me just get some space here. So your simplest binomial expansion, say we had 2 over 1 plus x, and we want to do this 1 plus nx plus n minus 1 over 2 factorial. This thing here, this is valid when this is between -1 and 1. So all we have to work out here is the equivalent condition for these two things here. And we have to take the tighter of those two constraints to get the validity overall. So just keep that in mind. I'm going to do that at the end and work through the expansions first. But this part of the question is never that hard, as long as you remember this. Okay, so what have we got? Well, we've got to start by writing it out into the nice format. So we've got f of x is x over 1 plus x squared plus 16 over 2 minus x. But there's a bit of manipulation before I can do the binomial expansion. I'm going to write it like this, x plus 1 plus x squared to the -1. So we're going to do a binomial expansion on this, and this is now good to go. But this one is not. So we've got 16 times 2 minus x to the power of -1. So 16 times 2 minus x to the -1 has to be forced into the following form. I need to have a 1 plus something. So I take out the 2 as a common factor and write it like this. That gives me 16 over 2 times 1 plus -x over 2 to the -1, which is 8 times all of that. Right, so now we're ready to start. And what I'm going to do is I'm going to do the binomial expansion on this bit, and then I'm going to do the binomial expansion on this bit here. Then I'll multiply it by 8, and I'll multiply the first one by x, and then we'll put them together. Just be careful with your setting out. Right, so the first one is 1 plus x squared to the -1. So this is equal to 1 plus nx plus n. So I always start by writing that out. But the thing in here is that this x and this x in my expansion is the x squared, right? So in here, we've got equals 1 plus -1 times x squared plus -1 times -2 over 2 factorial x squared squared. Now that's as far as I'm going to go because I don't have to go past x to the power of 4. So that one gives me 1 minus x squared plus x to the power of 4. And I'm going to be multiplying that by x. So we'll do that now. So x times that, and that needs to have an is roughly equal to x minus x cubed plus x to the power of 5. But actually we don't care about that. So we're going to have that going into the final thing. Now we have to do the same thing for the other binomial expansion. So we've got 1 plus -1/2 x to the -1. And that's roughly equal to 1 plus -1 times this thing here, -1/2 x plus -1 times -2. I'm just going to stop talking. Okay, so let's clean that up. Now, actually, it simplifies really easily. So it's 1 plus 1/2 x. This all goes away, and it's going to be plus 1/2 x squared. This goes down to a -1, so it's going to be minus -1/8. So plus 1/8 x cubed. The same thing with this, plus 1/16 x to the power of 4. And we need to multiply that by 8. So it's going to be 8 times this. Now we have to put them back together and we get this. F of x is roughly the same as, so what did I have from my first one? Well, I had x minus x cubed, and then over here I had plus x to the power of 5. I'm leaving those gaps because I'm going to put it into columns. So it's plus 8 plus 4x plus 2x squared plus x cubed plus 1/2 x to the power of 4. And so when I add that up, I get f of x is roughly equal to 8 plus 5x plus 2x squared plus 1/2 x to the power of 4, and I forget about the terms above that. All right, so the last thing we have to do is to look at the validity, and that's now straightforward because I've got my two expressions, very messily, but I've got them there, into the following form. This one has got 1 plus x squared to the -1. So let's write it out a little bit more tightly. F of x is equal to x over 1 plus x squared plus 8 over 1 plus -1/2 x here. So this one is valid for the absolute value of x squared being less than 1, which is the same as the absolute value of x being less than 1. This one is valid for the absolute value of -1/2 x being less than 1, which is the same as the absolute value of 1/2 x being less than 1. Finally, which is the same as the absolute value of x being less than 2. So which one of these constraints is binding more tightly? Well, it's this one here, right? I need to have both of these things being true, which means that our validity is valid for the absolute value of x is less than 1. So there you go. I've got 25 seconds to spare, but I'm going to stop talking now. Aidan, I really hope that helped. These are really fiddly. So have a look at the place value thing I've done here at the end. See, I told you I could talk for another 20 seconds. Look, this is going to make it harder to stuff up at the very last minute. Thanks for watching.